In this video, we're going to do another example of curve sketching using derivatives to help us. So the last example we had was a rational function. If you missed that video, go check it out. In this question, though, we're going to have a polynomial function. So f of x is equal to 3x to the 4 minus 12x cubed. And there's going to be some terms I throw around in this video, and if you're not familiar with them, go watch the first video. I explain them all at the beginning. So if you're not familiar with critical points, inflection points, local extrema, those types of things, go watch that first video. So what's the first thing we can do here? Well, we can try to take the derivative. I think that would be a good idea. And if you take the derivative of this, it's just a simple power rule. You end up getting 12x cubed minus 36x squared. Now, why do I want to take the derivative? Well, now I can set this thing to 0 and try to solve for x. What that's going to do is tell me the locations of my critical points. Critical points, of course, being my maximums, minimums, or potentially some inflection points. So how do I solve for x? Well, one thing you can do is factor this. You could factor out a 12x squared. You'd be left with x minus 3. And now you could solve for x, right? If this term multiplied by this term is equal to 0, then that means either this term or this term is equal to 0. If this term is equal to 0, it means that x is 0. It's the only way that can happen. And if this is equal to 0, it means that x equals 3, right? 3 minus 3 is 0. So either this has to be true or this has to be true in order for all this to equal 0. Now, these are going to be my critical points. We can figure out what the y values of these points are. So we'll do f at 0, so plug 0 into this original function. And we'll also do f at 3, so plug 3 into this original function. And those will tell you the y values at those points. If you plug in 0, you're going to get 0, right? 0 minus 0. So one of our points is going to be 0, 0. That's one of our critical points. If you plug in the number 3, you're going to have 3 times 3 to the 4 minus 12 times 3 to the 3. And if you do all that work, you follow your order of operations, what you're going to get is negative 81, meaning we have the point 3, negative 81 as one of our critical points. So this is fantastic news. We now have 2 critical points, which we're very happy about, right? 1 critical point there and 1 critical point there. So the next step would be to figure out, are these critical points maximums or are they minimums? Or are they potentially inflection points? We don't know. So to do that, we have to look at the double derivative or the second derivative, f double prime at x. Remember the first derivative, what it was? 12x cubed minus 36x squared. This is just a simple power rule. So I'm going to fly through this. If you don't know how to do the power rule, go watch the power rule video. But what you're going to get is 36x squared minus 72x. Now, we can figure out what the double derivative is at 0. So we're talking about this point. We're trying to figure out, is this point a max or minimum? And we're going to be able to do that by figuring out if it's concave up or down at that location. So let's plug in 0. If you plug in 0 there and there, you get 0 as an answer. And oh, lo and behold, if you get 0 as an answer, it's not concave up or down. Rather, it represents an inflection point. That's very exciting. So at the point 0, 0, we have an inflection point. Now, what about f double prime at 3? Plug 3 into this equation, right? Plug in 3 for x here and here. If you do that and you solve it, what you're going to get is a value of 108. Now, the fact that it's 108 doesn't matter. What matters is that it's a positive, right? Because it's positive, that means that it's concave up in that area, meaning that that point we found has to be a minimum point, right? Concave up means it looks like this, meaning that point we found is a minimum, not a maximum. So we have an inflection point and we have a minimum point. The other things that we could do would include looking for the other inflection points if there are any, right? Because remember, inflection points occur when the double derivative is 0. Well, we know one value of x where the double derivative is 0, right? When x is 0, but we haven't checked all of them, right? There might be other values of x that give us a double derivative of 0 as well. So let's figure this out, right? The double derivative of x, as we've said already, is 36x squared minus 72x. If we set that to 0, we expect to get at least one answer, right? One answer being 0, because we already know about that inflection point. But there could also be another inflection point, right? So let's solve for x here. You could factor this, right? You could factor out a 36x. You'd be left with x minus 2. And from there you could say, okay, either this equals 0 or this equals 0. So either x is equal to 0 from this, or x is equal to 2 from this, right? An x value of 2 here, 2 minus 2 is 0. That's why x could be 2. So we already knew about this location, but this is a new x value, right? So this is a second location where we have an inflection point. Now what's the coordinate? What's the y value at that point? Well, we'd have to do f at 2, right? Plug 2 into the original equation again. And if you were to do that, you should get as an answer negative 48, meaning the point 2, negative 48 is also an inflection point. So very exciting. We now have 2 inflection points and we have a minimum. So let's just take stock of what we have here so far. I'm going to draw my little x-axis here, my little number line, and I'm going to write down all the critical points we have. We have a 0, that's an inflection point, a 2, which is another inflection point, and we have our 3, which was our minimum, right? So this is an inflection point, this is an inflection point, and this is a minimum, okay? Now, these are all the important points that we're going to need. Because 3 is a minimum, we know that it's concave up in that area, right? It's concave up in this space because we said 3 is a minimum, right? Now 2, at the value 2, we have an inflection point, meaning that after 2, it's going to change. So if it's concave up here, at 2, it's going to change to being concave down. So over here, it should be concave down, right? Because you have to switch between concave down and concave up at those inflection points. That's what an inflection point is. Well, here there's another inflection point. So it's going to change again. It's going to be concave up over here. Okay, so we have almost everything that we need to graph this. The last thing we'll do, and you can technically do this step at the start of the question, you don't have to wait till now, but you can find your x and y intercepts, right? We already know one of the intercepts is the point 0, 0, right? That counts as an x and a y intercept, but there might be more x-intercepts, right? There could be many x-intercepts. So let's figure out what those are. X-intercepts. So to find the x-intercepts, we set y to 0 and solve for x. And we're using that original equation we were given, the 3x to the 4 minus 12x cubed. And you should factor this if you want to solve for x. You could factor out a 3x cubed, and you'd be left with x minus 4, right? Just common factoring there. Now, if you common factor this, you set it equal to 0, either this is equal to 0 or this is equal to 0. So either x is equal to 0 or x is equal to 4. It's the only way this can work. We're already aware of this point, right? The x-intercept at 0, but we were not aware of this point, an x-intercept of 4. So that means we have a point 4, 0. That is a point on our curve. So very exciting. We now have another point on our curve. I think now it's finally time that we sketch this out. Okay, so let's draw our xy axes. So we have our x here. Here we have our y-axis. Remember, make sure you're using a ruler, making this nice and neat. Let's talk about all of our points. We have the point 0, 0. That is our x and our y-intercept. We also have an x-intercept over here at 4. Okay. We have the point 2, negative 48. That is an inflection point on our graph. We also have a minimum at the point 3, negative 81. Okay, so these are all the points we know about. We also know where the graph is concave up and down, right? The graph is concave up. Go look at this graph again. The graph is concave up between 2 and, well, infinity. Everything to the right of 2 is where the graph is concave up. So if you're looking at our graph down here, everything to the right of 2 is concave up. So our graph is going to do something. I'm going to do my best to make this nice and smooth. It should just be a nice smooth curve. Goes up like that. Okay, so make sure that's nice and clear. We know it's concave down, right? In this section over here, in between 0 and 2, it's concave down. So between 0 and 2, so from this point to this point, it's concave down, meaning that it's kind of like kind of like this. So that's concave down. You can see that clearly. And you can see how this is concave up this whole time, right? It's getting pretty steep, but you can see this is all concave up, right? Now, to the left of 0, if you look at that chart again, it's concave up on the left. So to the left of 0, it's going to be concave up, so it's going to go like that. Now, let's just check and make sure everything is okay. We have that minimum value at x is 3. We have an x-intercept here at 4, an x-intercept here at 0. It's also our y-intercept. We have an inflection point here where it goes from concave down to concave up. We have an inflection point here where it goes from concave up to concave down. And I think just about everything is in order. So I would be confident in saying that this is your final answer.